Okay, can everybody see the screen okay? See my screen?
Yes.
Awesome. All right, so we're gonna go ahead and get started. I guess everybody's been doing Zoom for a while, so shouldn't be any problem, but go ahead and say it. Go ahead and mute yourself unless you're talking or asking a question. And and ask questions, just go ahead and shoot as we're going through this. There are absolutely no dumb questions. This is an intro to cooling, so this is just a basic introduction to what the cooling systems are and how they work. And then as I mentioned, in case you didn't see the post, there'll be a follow-up to this, a part 2, where we get a little more in depth with design and the physics and thermodynamics and fluid mechanics and design and modeling. First of all, what is cooling? So cooling is the cooling system just gets rid of heat, either from the engine or from the air intake or from electric vehicle motors. And the reason why we need it is that internal combustion in electric vehicles are not perfectly efficient. So in internal combustion engines, only about a third of the energy goes to the wheels or to mechanical energy, and the rest, the other roughly 2/3, is heat that goes out the exhaust and through the coolant or oil. So about 1/3 of the heat has to be rejected through coolant and oil. And an electric car, being more efficient, is maybe roughly 10% is waste heat. And I guess I'm going to go ahead and say I do have some stuff in here regarding electric vehicles, but that's not really my background or specialty. So feel free to ask questions. I'll try to answer them the best I can. And if I say anything that's just patently wrong, feel free to chime in and correct me. So again, why the reliability of vehicles? There's physical limits to the material. If we can't get rid of that waste heat, the engine will melt, the valves will break down, you'll burn holes in them. Fuel will knock, those pre-ignition, if the combustion chamber gets too hot. Oil breakdown, there's a breakdown in lubrication and the engine will seize up. In electronics, there's a breakdown in semiconductors and insulators, causing short circuits. And then it also affects performance. If we can cool down the intake air charge, we can get more air into the engine to burn more fuel, and we can safely run higher combustion temperatures. We can maintain our optimal oil viscosity to reduce friction and help with lubrication. And then if we do it right, efficient cooling means there's less weight and drag if we optimize our cooling system. And reliability, I don't know if you guys have probably all seen or heard of the Bahamula, that a team entered a Baja car that they converted to a Formula car, and they ranked in the top third, even though they were running a lawnmower engine, which is, you know, less than half the power of probably every other vehicle there. So if you don't cross the finish line, you're not going to win. So cooling engines, internal combustion engines, there's kind of two types. There's liquid cooled engines and air cooled engines. Liquid cooled engines circulate a fluid through the engine to cool it down, and air cooled engines have lots of fins and air passes over it. Air cooled engines anymore are kind of relegated to smaller engines, motorcycles, lawn equipment, and airplane engines. The main reason for that is with higher performance engines, there's and packing more cylinders closer together, it's hard to get enough cooling fins in there. And then also liquid cooling enables us to control the temperature more precisely, where an air-cooled engine, the temperature is going to fluctuate a lot depending on the power demand. Air-cooled engines are often lighter than liquid-cooled engines, though, as a caveat. So throw in air-cooled engines in there for our Baja brothers, but for the most of this, we're going to be talking about liquid cooling. So to start with, how liquid cooling happens, there's water jackets surrounding in the engine, surrounding the cylinders and around and up in the heads, around the valves. The valves specifically because the combustion chamber and the exhaust valves are the hottest part of the engine. The temperatures can get in the thousands of degrees in the combustion chamber. So in order to keep the engine components from melting, we need to make sure we get good water circulation through there. On the right here, we have an engine block with water. You can see the water jackets around it. And then the head, and where the head and block meet, the water jackets connect, and there's a gasket known as a head gasket in there. And often you'll hear about a blown head gasket. When that happens, water can leak into the cylinders and cause catastrophic failure because water does not compress like air does in a cylinder. The water is circulated through all these jackets and through the engine through a water pump. There's mechanical pumps that are driven either off of a pulley with a belt, or they're directly connected to a shaft. And then there's electric pumps, which are controlled electrically, obviously. The pros and cons to those, mechanical, you're not wasting the conversion from mechanical energy to electric energy and then back to electric energy to mechanical energy to power the pump. The benefit to an electric pump is you can more precisely control it, and you can eliminate some of the unnecessary drag at high RPMs that are going to be there with a mechanical pump. And if you spin a mechanical pump, if you spin a pump too fast, it's going to cavitate, stop pumping altogether, and start eating itself. And that's bad. So once there's radiators and heat exchangers that the fluid is pumped through, and that air flows in one direction and coolant flows across in the other direction in tubes. Air flows, they add fins to increase the surface area that the air flows across, because air is not a very good conductor and does not have a relatively high heat capacity. And that's how we reject the heat from the engine. The heat is pumped from the engine into the radiator, and then from the radiator into the environment, to the air and the atmosphere. Thermostat controls the temperature of the engine and the water flow. There's mechanical and computer controlled ones. Excuse me. Mechanical ones function. There's a wax material that expands and contracts with heat. And as it expands and melts, it's gonna open the valve to allow water to flow. And then when at the specified temperature for the engine, and then as it cools down, it's going to close, and the water will just continue. Instead of going through the radiator, the water will just continue to circulate through the engine. It's important that circulation continues to happen, because if water sits in one place in the engine, specifically around the valves and the combustion chamber, it's going to get too hot and it's going to boil over. And computer controlled is ideal. In a lot of situations, you can more closely control the water flow, and that is used in conjunction with an electric water pump. There's a pressure cap and an overflow tank. The pressure cap on a cooling system is used to increase the pressure of the system and increase the boiling point of water. If water boils in an engine, it's going to create air pockets around the hottest part of the engine, and then those parts, air is not, like I said before, is not a good conductor. It doesn't transfer heat well. So those parts are going to get hotter and hotter until they melt. And this also serves to allow the coolant, the fluid in the system, to expand. It's the fluid, water or coolant is not compressible. So if it were to just keep expanding and expanding, the pressure would build up, be very high, and you would blow seals or break parts. So as we see down here, the coolant expands, and the radiator cap allows the coolant to flow out. It maintains a constant pressure in the system. Usually anywhere from 5 to 20 psi is common. And then as it cools down, it also allows the coolant to, it allows it to siphon, the system to siphon coolant from the tank back into the system. So it doesn't create a vacuum as it cools down, because when you create a vacuum, that's a low pressure, and coolant or water boils at even lower temperatures than it would at atmospheric pressure. And I already talked about coolant sum. Typically, your coolant is going to be a mixture of water and ethylene glycol or propylene glycol. And that's this green or sometimes orange fluid, different colors, with that sweet taste that cats love. It is poisonous, so don't drink it. Don't let your cats drink it. But here's a chart that kind of talks about the different ratios and how that affects the freezing point and boiling point. So coolant in colder climates keeps the water from freezing in your engine. If it freezes, it's going to expand and close off passages, and it will pop out your freeze plugs, which are designed for that purpose, so it doesn't actually break your engine. There are some performance coolants that also increase the conductivity of the coolant, because propylene glycol, while it does increase the boiling point and lower the freezing point, it doesn't conduct heat as well as water does. So there are some performance coolants that are designed to help keep that heat conduction high. So now, where is radiators are most commonly, as you've probably seen most of your cars, in the front. The reason we do this is there's get maximum airflow, it's close to the engine, and sometimes it's done for weight distribution. That's why, like, even in like Porsches and things like that, where the engine is in the back, the radiator is still likely to often mounted in the front. On the sides, and like the formula cars, side pods, this is good for aerodynamics and weight distribution. You can see down here, this radiator is mounted almost sideways, almost parallel to the airflow. And this is so we can get a massive radiator in there, but not have a lot of drag. The side pod doesn't have to be super wide. And then also in Formula One cars that are moving incredibly fast, it allows the airflow to go through a small passage, expand and slow down, so it can actually absorb heat through the radiator and then speed up again. So it also helps a lot with aerodynamics. We'll get into that more in part 2 of this. And then in the rear, there's also sometimes the radiators will be mounted in the rear of the car for weight distribution or protection in off-road racing, or where there's lots of rocks getting kicked up, or if you're racing where you're going to run into stuff a lot and you don't want to smash up, and you might smash up the front of your car. If you break your radiator, it's kind of game over. And then there's oil cooling. So this is still kind of part of powertrain cooling, but there's also transmission and differential coolers as well. So I'm kind of tacking these on too, even though these aren't kind of part of the typical main system. Some engines don't have the separate cooling systems, but like ours, the Formula car does. A lot of motorcycles will, and then most automatic transmissions will, and then high performance differentials and transmissions will have coolers as well. There's air intake cooling. This is done for forced induction when turbos can create, like compressing the air creates a lot of heat, and then just because they're driven off the exhaust also adds a lot of heat. So they want to cool that air back down before it goes into the engine so they can pack as much, it gets dense, and they can pack as much air into the engine as possible. For electric vehicles, electric components, as I said before, get hot. There's inefficiencies in waste heat. There is some air cooling similar to the regular engine where there's just fins, but most electric vehicles now and their components are being liquid cooled, just because the high performance nature of them, and then so they controlling that cooling allows them to run more efficiently and optimally. The electric motor will have a coil going around it, and then some newer motors also incorporate heat pipes, and heat pipes are an even more efficient way to transfer heat. They're really lightweight and really fast. They transfer the heat really fast, but they work well in electric systems and motors because the geometries are a little more simple versus a combustion engine where it's you know, the engine is like, the motor is likely cast, and there's all kinds of odd shapes and galleys and passageways and channels that aren't conducive to heat pipes. And then similarly, that fluid is going to be pumped out. Oh yeah, here's a little more on heat exchangers and heat pipes. I'm not going to go too in depth on the technology there. Maybe next time we'll look a little closer at that. This heat exchanger just has passages milled in it for the water to flow. And this is a block on the right that would be attached to your electrical component, and the heat pipes getting the heat out to a large heat exchanger. Yeah, heat pipes or liquid cooling still works in conjunction with the same type of radiators that you would have with on a combustion car. The radiators function very much the same as far as getting the heat out into the atmosphere. All right, yeah, like I said, I'm gonna get a little more in depth in part 2 of this. So we'll announce that at a future date. But any questions? I guess I went through that really quick. I hope I didn't leave anybody behind.
Yeah, I have a question actually.
Can
we go back to the heatsink part with the fan for the electronics? Yeah, there you go. Here, the air-cooled one. So on this left image, is the reason they always usually put the fans in that direction is just because of packaging? But usually, I mean, I guess that will distribute air through the fins, right? You don't want it to go towards the fins. You want it to go through the fins.
Right, exactly.
Okay. I just wanted to, so it's usually packaging, but ideally you would put it like through the side, right?
Right, yes. Yeah,
okay.
In this case it was probably packaging, but yeah, the idea is to get the air to flow through the fins.
Gotcha.
And then I guess I didn't really go through this picture on the side, but here's kind of an electric vehicle situation. The radiators are side mounted. This is from a Formula E vehicle. The motor controller dumps a lot of heat, is mounted up here on top. This is the motor down in front. You can see all of this has plumbing going to it. And then the batteries as well are cooled. It's because they're offloading a lot of energy very quickly.
I have one question.
Yes.
Oh yeah, so like on the right side of photo, like usually most of the car, you know, like when you see the car, like I mean, the radiator is right from the engine. So like so here's the radiator size next to the engine, right?
Yes.
So like it's only for like a Formula car. Does it have like those kind of things?
Mm-hmm. I'm sorry. Say that your question again. I missed that.
like so like most of the car, you know, what the radiator is right in front of the engine.
Uh-huh.
Yeah, like on the right pitch. I mean, on the pictures, when you see it, the radiator is like on the side. So what is the difference?
Okay. Yeah, good question. So I kind of went through that part pretty quick. I'll go back to it. So where the radiators are mounted in the car is often depends on, you know, this design decisions. So you were saying a lot of times that the radiator is mounted right in front of the engine.
Yeah.
And that is the most common placement for it. Front of the car is getting blasted with air, so that's a good spot for it, as you can see on the right.
Yeah.
In Formula cars, like this one, they put them in the side,
On the side.
right on the side of the vehicle. By putting them in the middle, that helps with weight distribution, moving some of that weight to the middle of the car, brings
Oh, okay, got it.
brings it closer to the engine because the engine is behind the car.
Oh,
And
yeah.
And it also allows the front of the car to be more aerodynamic. They're going to put that big wing out front to get a lot of downforce. And then they can, at a lot higher speeds, they need the car to be very aerodynamic because the aerodynamic drag is huge at high speeds.
Oh, got it. Yeah. Thank you, man.
Yeah.
I have a question. So you mentioned both water cooling and oil cool. How are they different?
So water cooling and oil cooling are different in terms of like the different systems of a car. So water cooling is used in the engine to cool the engine, to do most of the engine's cooling, because water is a very good conductor of heat and has a very high heat capacity. So it can get rid of heat and move heat very efficiently. Oil cooling is done specifically, not so much to cool the engine, even though it does do some engine cooling. About roughly 10% of the engine's heat is, and I see if I can go back to the oil cooling. Yeah. About 10% of the engine's heat, give or take, will go out through oil if you're using oil cooling, but mostly oil cooling is just for the purpose of cooling the oil to maintain the lubrication and to keep it from breaking down. So does that answer your question, or?
Yeah.
Okay, cool.
So would in these oil coolers, would you still run the oil doesn't run through these, does it? It's just a different coolant loop for just the oil, like a different oil jacket, or the oil would run through these?
The oil would run through these. So there's a oil pump in the engine that pumps oil through the engine. And then to cool it, it's the oil's taken outside of the engine for an oil, I guess, yeah, I burned through this pretty quick too. On the left here, there's an oil to air where the oil just passes through a smaller radiator. Because like I said, it only handles about maybe 10% of the engine heat coming through here. So it's smaller. And you can see it here sitting in front of the main radiator. And that the heat is rejected to the atmosphere through the air, just like the water, the heat is from the water. And then on the right, there's some oil to water coolers or heat exchangers where you can see here there's two sets of coils where water will flow through the outside and the oil will flow through the tubes on the inside. And that heat will be transferred to the water coolings, to the water of the main engine cooling system, and then rejected through the radiator. Some of the benefits of this are that the water is a better conductor, is more effective at moving heat than air is. So you can put this, it's smaller, and you can put it closer to the engine or mount it in some obscure place. And then the downside is that if there's a failure again of this oil to water heat exchanger, you may have oil and water mixing, and that's bad for both your cooling system and your lubrication system. But yes, oil does flow through these, and it's, yeah, like I said, pumped out of the engine, goes through the cooler, and then is fed back into the engine. Did that answer the question?
Yes, thank you. Actually brought a curiosity question. If nobody else has questions, I know I'm asking a few here. So would there be any pro or benefit I'm trying to think about it. I just came up with the question, but if so we said like water is much better than air, right? Probably I think like 4 times or something.
Yeah,
So
right.
yeah. So would you, in theory, if you had space and whatnot, would it be beneficial if you have a radiator and an oil cooler, except you run your coolant through the oil cooler and then the water around the jacket of your oil cooler through a radiator?
I'm sorry, say that again. I missed that
So like
last part.
basically add an oil cooler, but put coolant rather than oil through, and then have a radiator for the oil cooler. Like basically how the way
Oh,
this,
okay. Yeah,
yeah,
you could
is that
you could you could do that. That would just be like an intermediate heat exchanger. Um,
would,
uh,
would it be redundant, or you think it would be
it,
some performance improvement?
I think it would be.
I know it depends on the
Yeah,
radiator.
it kind of depends, and that's a good question. They do. It's kind of like to segue out of automobiles. They do that kind of intermediate heat exchanger a lot in HVAC systems and like nuclear power plants and things like that, where they really need to maintain the purity of the water and keep the system separate. So in doing that, I think it would be a little bit redundant. It would protect your coolant. If there was a failure, it would protect your coolant from getting oil in your water cooling, but it wouldn't protect the oil from getting water in it. And you would still have a separate radiator. So I think it would be a little bit redundant, but that is a.
What do you think would improve performance?
In terms of performance,
Yeah.
I don't know that there would be much gain in performance from pumping, because if you're just running the oil through the air cooler, you're pumping the oil all the way up to the front, and then if you're versus having an intermediate step where you're pumping the oil to the water, and then you're pumping the water up to the front of the car. That heat transfer is gonna depend more on the pumping rate, how fast you can pump that heat, that oil or that water up to the front. And then also there's gonna be a little more thermal resistance by putting that intermediate barrier of aluminum in that or copper in that heat exchanger between the oil and the water. So you're adding one more thermal resistance to the system, which would decrease the heat transfer rate. Does that make sense?
Yes. Thank you.
Yeah. Any more questions? I can kind of roll through the slides again, see if anything pops back into your head, but
Oh, I just had a quick comment about the water wetter.
yeah.
So I was actually talking to James about this a few weeks ago. So water wetter actually does what it says on the bottle and makes water wetter than it is, which sounds kind of weird, but wetness is measured by how much a liquid like spreads out on a surface when you put it on a surface. And water has pretty high surface tension, so it's actually not that wet. So milk is actually a lot wetter than water. So water wetter is like a surfactant that breaks up the surface tension of the water in your cooling system, so you have a lot less air pockets, so there's more direct to water conduction.
That's a great point. Absolutely. Especially in like cast blocks and engines where the surface is really rough. The water naturally won't want to get down into all those little grooves and valleys. And so, having something with very low surface tension will really help it keep bubbles from forming and help make good contact between the engine block and the coolant. So really good point. And that is to say, all that said, we don't get to use any of that stuff because for formula and combustion anyway, we're only allowed to run water for cooling. So no additives allowed. which is fine because water's all right and it's clean and it's easy and it does a pretty good job. I guess I should mention, if you are just going to run straight water, it's very important to only use distilled water. Any minerals are going to foul your system. It's going to kind of accumulate on the inside of your radiator and on the inside of your engine, and it's going to prevent the transfer of heat. It's going to add a lot of thermal resistance, and that's something we'll talk about a little more next time in the design part. But yeah, it's good to say that don't just run tap water or any old water through your system, because those minerals will accumulate and clog your radiator and cause things to corrode.
I guess if nobody else has a question, I have one more question.
Yeah, shoot.
I don't know if this is part of your next one, but if you can go to actually either this one or the EV one, actually, there you go. So assuming, you have this loop going through your radiator, your pump, your motor, and then it seems like your battery pack. So it's like a whole different other jacket as well.
Mm-hmm.
So I know, since you're not really you're probably sourcing components together, and then there's restrictions through every single component you go through. Is there any technique or something like that you design technique or anything like that to address these restrictions, or the motor restriction, and you just kind of have to either deal with the pipe size or the hose size, or is there tricks for that?
Yeah, so there's a few different ways. One is you can I think a more common one is maybe each of these separate systems will have its own cooling system with its own pump and its own heat exchanger or radiator. Is one way to do it. Another way to do it is just to run a bigger pump that can handle the flow and all the restrictions. And then another way to do it is to run the components in parallel. So there you have a lower system pressure overall head in the system, but and it makes it. But you need a higher flow pump to handle that, even though there's lower pressure. So there's a few different ways to deal with that.
Like a parallel loop, you're saying?
Right.
Okay. I guess wouldn't that be more I guess it comes into I guess that's for the next workshop. I don't want to get ahead here, but yeah, so okay.
Yeah, no, I mean, we'll definitely cover that in the next workshop, but I mean, we're done, so feel free to ask away, or if we want to discuss it now, that's totally cool too.
Well, since fluid will follow the path of least resistance, I'm sure parallel loops would be a little more complex, I guess,
Mm-hmm.
into distributing the lengths and how do you figure out, I guess, I don't know. Yeah, I would see an issue through the flow rate will be a lot lower if you're using one pump, even if the head is enough or whatnot to a certain one, how, I'm not sure how, I guess that's the next presentation.
Yeah, so if you're running them in series, just the kind of continuity, the laws of physics that the same amount of fluid is going to go through each one. But you're right, in parallel, you do have to pay more attention to the pressures and use valves or orifices to control the pressure and flow. So maybe adding a little more resistance to flow to components that don't have a lot of resistance, so that they maintain even flow across each of the components. Or you can use that to your advantage as far as that different flow rate or amount of flow to channel lots of flow to your components that need to reject a lot of heat, and just a little bit of flow to the components that don't maybe need to reject as much heat. But it is really complicated and easy to introduce problems with parallel flow systems for that reason.
Got it. Thank you.
Yep. Right. Any more questions? If there are no more questions, I guess we'll.
I had something.
Yeah.
Do you have any comments to make about, say, ducting or ducting methods?
Yeah.
Best practices.
Yeah. So let's go back to side mounting here, because they do a lot of ducting with this, and this is kind of our situation in formula. So did you have any specific questions about ducting?
Kind of looking for general best practices. And then I was also curious, I've seen a lot of teams run rear-mounted radiators and without any ducting either on the top or side to the radiator. And I guess that kind of just confused me how they even could get enough cooling that way.
Yeah. Again, that's going to be the aero. There's a benefit of putting the radiator behind the car, is that you can make the car even narrower with less drag. But you do have to, you know, in designing the aero of your car, make sure that you get enough air back there, or rely on fans. I can't believe I didn't put a fan slide in here. What is wrong with me? There's commonly a fan connected to the radiator too, to boost airflow when the car is either not moving fast or there's just a really high demand. There's not enough air supply and there's a really high demand for cooling. The fan can kick in to help out with that. So that is likely a big source if it's mounted behind the car rather than in the side pods. And then in the side, like I said in this picture down here on the right, oftentimes to make the car narrower and keep the drag down, the radiator will be mounted at an angle or sideways, so that the because I mean, you can see here, this is a massive radiator, and if you were to have it facing into the wind, it would create a ton of drag. So, and then your ducting, as far as working with aero, that's going to be a big balance, and kind of something that the cooling team and the aero team have to work together on. And we'll get into this more next time for sure. But is because of that, there's the balance of, all right, well, we got, you know, we're minimizing drag because we got, you know, this small opening and we're pretty narrow, but we got this massive radiator, and it's going to be a lot of weight because maybe we're not using our air efficiently. Whereas if we got to use more air, there'd be more drag, but we could use a smaller radiator and there would be less weight. So those are the kind of optimization decisions that have to be addressed for sure. And then aerodynamics, a lot of times you can see that on this bottom left picture, the air intake here is up high because a lot of the air will be flowing up over the front wing element, and they're trying to catch some of that, but it's relatively small, so you get that high speed air. But once it gets inside, the side pod opens up and that air is allowed to slow down so that it can go through it can develop higher pressure, and then also go through and go through the radiator slowly and pick up more heat. A lot of the designs will have the side pods openings or the duct openings for the radiators just really close to the side of the car to catch some of that air that's following along the body. And then also to minimize the width of the side pod, how far out, and minimize drag. So that's all just kind of have to be decided on and factored in when you're doing your overall aero package design and making those decisions. There's also some cars will, rather than on the side, have a intake at the top of the car, like this one over here. This may be used for the intake, or it could be used for some other cooling, be it oil cooling or electronics cooling or something like that. But there's often an intake at the top of the car, just above the driver's head. And if you were going to put a radiator behind the car, that could be a good place to get some air from.
Thank you.
Yeah, good question. All right, any more questions? I'm gonna do the slow roll to the end of the slideshow, like the silent 5-second countdown before we end this thing.
I have one more.
All right.
More. That's the last one, I promise.
Yeah.
So on a cooling loop, I understand that with like higher flow rates, you'll have like higher pressure drops and so on. But if you have a component that can handle the least amount of, like its seals or whatever, can handle the least amount of pressure in your system,
right?
You would put that at the beginning of the loop, right? Not at the very end after all the pressure drops. You would put the one with the lowest sort of pressure handling towards the beginning of the loop, or
it really wouldn't matter that much, because it's kind of analogous to like the flow of electricity, where if you have a bunch of resistors in series, right, like it's not like there's it's going to be a pressure differential across that component. So before and after it, there's not going to be whether it's at the front, whether it's at the beginning of the loop or the end of the loop, that pressure differential is going to be the same across that component. However, there is a difference in overall system pressure. So in that case, you would want to find the lowest pressure part of your system, and that's going to have to do with the pump and where your radiator cap or pressure cap is, where those two things are in relation to each other. You can find a low pressure part of your system to put that component in, and hopefully it aligns with your packaging and plumbing. Okay. Hopefully it fits in, but
okay, because I thought like let's say if I had two components that, let's say they create a back pressure of about 20 psi and they're in series, and then there's one component that can handle like 5 psi, you know, that's peak. Would that, like you're saying, it doesn't matter where you would put it in the loop?
Right. It's in relation to the other components. It's not going to matter, because it's going to have the same pressure drop across that component, no matter whether it's before or after those other components. But it does matter in terms of like in relation to the atmosphere, because it's a closed system. So the absolute pressure will be different in different parts of the system. But that's in relation to the inside of the system and the outside of the system, rather than the inlet of the component and the outlet of that component.
I see. So safety wise, like seals and whatnot, I mean, yeah, okay, I understand what you're saying. Yeah. Okay. Thank you.
Yeah. That's a really good question for sure. And I think I'll make sure I get into that next time, because
excited for the next one.
Yeah, for sure. You can blowing out seals and have your leaky system. Oh, let's see. We got chat. Haven't been looking at chat at all. Oh, you guys have been chatting with each other. Okay, cool.
I have a last question for you, Dan.
Yep.
So, again, we can keep this pretty short, like top level. But if you were tasked, as you have been, with designing a cooling system, what are like the first steps you would take? Or like, how would you start? Because I think with cooling, there's so many variables. You got aero, and you've got different engines or powertrains that you're trying to cool, and you've got different radiator sizing. It's like there's too many variables to start with sometimes. Yeah. I'm just wondering, like, if you were to set out and start designing a system, what approach would you take?
That is a really good question. Gosh, off the top of my head, like hesitant to give an answer just off the top of my head because I might be wrong, but I guess it would be looking at designing a system, looking at the requirements, like the engine, and then also the layout of the car for packaging, because those are the amount of heat you have to reject, and also the packaging were the two biggest constraints that we ran into. So if we have those in mind from the beginning, it can be, I think it would be really, really helpful. That did bring up something I didn't mention that I feel like I should have. And actually, it just totally slipped my mind while I was answering that question. So, unfortunate. But yeah, that's good. In terms of starting to design, I would, yeah, look at the layout of the car, the packaging, and the requirements. And yeah, there is a lot of factors. So that's it's a hard one to answer off the top of my head. But I'll it's a really good question, and I'm gonna I'll think about that some more, and I'm sure we'll get into that. I'll try to make a point to get into that in part 2 of this when we actually start talking about the design and some of the finer details.
Mm-hmm. Yeah, I think you kind of have to start math. That's probably where you need the equations and whatnot. So makes sense.
Yeah, but really good question. I know just going through and making this presentation and part 2 of this presentation, there's a lot of the stuff that like I wish you would have known and paid closer attention to and spent the time going over when we started the project last year. You know, I feel like it would have been really helpful. So hopefully this will be helpful for the next go around.
Yeah, definitely. Yeah, thank you so much, dude. It's been great.
Yeah, thank you. This was very helpful. I learned a lot.
Thank you.
Yeah. No, thanks for coming, everybody.
Yeah,
Thank you.
And if you have any questions that come up or anything that pertains to your systems that you run into, feel free to shoot me a message or an email or hit me up on Slack.
Yeah, for sure.
All right.
Thanks, Daniel.
Have a nice weekend.
Yep. Everyone have a great weekend.